Hi, and welcome to MSc. In this video, we're going to be looking at primary trigonometric ratios, specifically comparing angles in standard position to the reference angle. So to investigate this, we're going to look at this example of an angle in standard position, which again is defined from the positive x-axis counterclockwise around to the terminal arm. So there is our theta value. Our phi value is between the x-axis and the terminal arm itself. That is my phi value. This point here is my terminal point for my terminal arm, and the coordinates of this terminal point are -8, 5. From this, we can look at drawing a right triangle here, and we can say that our x value is -8, our y value is 5, and we could calculate the r using Pythagorean theorem if we wanted to as well, or if the question required. Using though x and y are opposite y and are adjacent x, we can calculate phi using tangent. So let's do that here. So we can say that the tangent of phi is equal to the opposite side over the adjacent side, which will be y over x. Rearranging, we can say that phi will equal the arctan, which can also be written as the tan inverse, tan to the -1, of y over x. So we can say that this is equal to the arctan of 5 over -8. And in doing that here, you'll get a negative value, and it should say -32.005, which we are going to approximate as just -32. Now, we've said in a previous video that phi is generally taken to be the positive value, and the reason this is negative is because of the -8 that we put in. So we're going to say here, okay, well, the absolute value of phi, the size of phi, is approximately 32 degrees. Okay, from that, I can determine the theta. I can say my theta value is going to be 180 minus 32, which is telling me that the theta is going to be 148 degrees. So we're able to calculate our theta in that way, which is great. Now let's look at something interesting that's going to arise here. So let's look at sine of 148. And if I take the sine of 148, I'm going to get 0.5299 ... It's going to continue on. Okay. Let's compare that to the sine of phi of the 32. And if I do that, I'm going to get 0.5299 ... So they're the same. That's interesting. Let's see if that happens to the other ratios. So let's look for cosine of 148. Well, if I do the cosine of 148, I get -0.848 ... If I look at the cosine of 32, the negative goes away, but I'm left with the same decimal, the same ratio. So there's definitely something going on here. Let's look at the tangent now that we used originally to calculate this. Tan of 148 is -0.6248 ... If I do the tangent of 32, I get positive 0.648 ... Oh, okay, so it appears to me that with all of these being our theta values and all of these being our phi values, that there's a relationship here. And what we can say then is that it appears as though the size of sine phi, or theta rather, is equal to the size of sine phi. And in this case, they were actually equal, not just the size of them. But we can also go on and say then that the size of cosine theta is equal to the size of cosine phi. They're going to produce the same ratios for all three primary trigonometric ratios. This means that there's this strong relationship, and if I solve for phi, I can find theta, and we've already seen that. But it also means that the ratios are equal in size. So why was cosine and tangent negative here? Well, that comes back to the cast rule that says cosine's positive there, they're all positive here, sine is positive here, and tangent's positive here. And so the ratios that we get out of these are the same size. And so we're able to determine one and then say it's equal to the other. The sine was positive in both cases because we were in the second quadrant where sine is always positive. With cosine, it was negative because cosine's negative there and tangent's negative there. But with the reference angle being 32, your calculator thinks that's an angle in quadrant 1, and it gives you the positive ratio. So let's take a look at what this practically means. It means that if I'm given a value, such like cos 120, well, I might not know what that is off the top of my head, but I now know that the size of it has to equal the size of its reference angle. And so if the reference angle is going to be cos of 60. Well, I know cos of 60. I know that the cos of 60 is 1/2. So cos of 120 is 1/2. The question is it positive or negative? Because this just tells me that the theta and the phi, the ratios are the same. It doesn't tell me the sign, but the cast rule does. So it tells me that I'm at 120, which is in quadrant 2, where cos is negative. So cos of 120 would be negative 1/2. Likewise, I know that sine of 300, the size of it has to equal the size of sine 60. Well, sine 60 is also one of my special angles, right? And so sine of 60 is going to be √3/2. Angle 300 is in the fourth quadrant. So sine is not positive in the fourth quadrant. Cosine is. So sine of 300 has to equal negative √3/2. And as our last example, we know that tan of 225 has to equal tan of the reference angle, the size of it. Well, the reference angle here is 45 degrees because it's always with respect to the x-axis, and it's 45 degrees beyond 180. Well, I know tan 45 is just 1. So this is the absolute value of 1. Well, in quadrant 3, tan is positive. So 225 is just 1. The tan of 225 is just 1. And so having this relationship between the ratios that are produced with theta and phi being the same size allows us often to convert from an angle that I don't know a lot about to an angle I know maybe a special angle for. It also means that when we enter angles into our calculator, we're going to get some that are negative, some that are positive. And sometimes we'll get two answers and we'll have to decipher, is it a positive answer or a negative answer that we actually should have obtained? And that leads to this being a more challenging topic than what you might have seen with trigonometry in the past. I hope this run through of reference angles and angles in standard positions and their relationship has been helpful. Thank you very much for listening and watching.